So in the last video, we obtained this formula for the length of a curve. So if C is a curve parameterized by a vector function out of t, which is equal to x of t comma y of t, where t is between a and b, then the length of C is given by the integral from a to b of the quantity square root of dx dt squared plus dy dt squared. So let's apply this formula for the following curve. So let's say C1 is the curve parameterized by the following. So x is cosine t, y is sine t, t is between 0 and 2 pi. Now we know that C1 is a circle of radius 1, and it is traced exactly once. And C2 is given by x is equal to cosine 2t, y is equal to sine 2t, t is between 0 and 2 pi. So we know that C2 is also the circle of radius 1, but C2 is the circle, so C2 is the circle that is traced twice because of that 2. Now, if you don't remember that, you can go back to one of the previous videos where we discussed the parameterizations of a circle. Now, what is the length of C1? So the length of C1, according to this formula that we obtained, is that the length of C1, so it'll be the integral from 0 to 2 pi, okay, then the square root of dx dt. So what is the derivative of x with respect to t? Well, that's negative sine t, and then if I square that, I'm going to get sine squared of t. Plus, it'll be dy dt squared, so dy dt would be cosine t, so if I square that, I get cosine squared of t. So this would be the length of C1. And sine squared of t plus cosine squared of t, that's just 1. And so the integral from 0 to 2 pi of 1 dt is 2 pi. Now if I look at the length of C2, according to and if I apply this formula right here, then I would be writing the integral from 0 to 2 pi square root of dx dt squared. So dx dt here would be negative 2 sine 2t, and if I square that, I'm going to get 4 sine squared 2t, and then plus dy dt squared. So dy dt here is 2 cosine 2t. If I square that, I get 4 cosine squared of 2t. And now here, if I factor out the 4, then I get sine squared of 2t plus cosine squared of 2t, which is just 1. So here I simply get square root of 4, which is 2. So then I get the length of C2 would be integral from 0 to 2 pi 2 dt, which is equal to 4 pi. So notice that if I am trying to find the length of the circle of radius 1, then I shouldn't be using the second parameterization, because this is giving me twice the length of the circle. However, if I am thinking of the circle as the path of a moving object, and the object is tracing the circle twice, then this is going to give us the distance traveled by the bug. So in terms of distance, this would be okay. But if we are strictly finding the length of the curve, then we must use the first parameterization here, not the second one, because the second one traces the curve more than once. Okay, so let me stop here. In the next video, we will be looking at another example to find the length of a curve in the 3D space.